In this video, we're looking at Bronsted-Lowry acids and bases, the all-important definitions, and considering what makes a Bronsted-Lowry acid and a Bronsted-Lowry base. The definition of an acid has developed over time. Many of the earliest acids known came from solutions of non-metallic oxides. These are acidic oxides, as we shall see. This led to a belief that acidity was related to the presence of oxygen in a compound. This theory was then falsified. One new observation disproved it. Hydrochloric acid, HCl, had been discovered. No oxygen present. A Bronsted-Lowry acid is a proton or hydrogen ion donor. A Bronsted-Lowry base is a proton or hydrogen ion acceptor. As you'd expect, they're opposites to each other. Bronsted-Lowry acids must have a hydrogen or proton that can be released as an ion, H+. This happens when the hydrogen is part of a weak bond or a polar bond. If the acid has one hydrogen, it can donate. It's called a monoprotic acid. Looking back up for a moment, HCl, hydrochloric acid, is monoprotic. Sulfuric acid, H2SO4, is a diprotic acid. The hydrogen ion released does not exist on its own in a solution, as it's always accepted by another species. Well, if that species accepts the hydrogen ion, it's acting as a Bronsted-Lowry base, and it could be water. If it is water, a hydronium ion forms. Generalized formula for an acid, HA. If that HA donates H+, it could be taken up by water, H2O. And if that happens, I'll get H3O formed. In this case, the water, in accepting the H+, is behaving as a Bronsted-Lowry base. The product formed is known as a hydronium ion. What's left from HA becomes A-, negatively charged because a positively charged hydrogen ion came away. A stands for anion. The above equation can also be written as HA as a liquid breaking up to give H+ and A-. That's a simpler form, and it's one we often defer to, but it's important to realize that in solution, an acid will be donating its hydrogen ion, which will be taken up by water. A proton in aqueous solution can be represented as both H+ or H3O+. Either will do. The acid HCl combines with water. We've seen that the water can accept the hydrogen ion and become H3O+. We can also simplify this and regard the proton as being produced straight from the acid. Cl- is also formed. When acid molecules break up into ions, we call it dissociation. Hydrogen ions are often called protons because they come from hydrogen atoms which have lost their only electron. Just a proton is left. Hydrogen atoms have one proton and one electron. If they've lost their only electron, just a proton is left, so it's okay to refer to a hydrogen ion as a proton. Other molecules are said to be acidic because they react with water to form an acid. For example, sulfur trioxide. It's called an acidic oxide because of the reaction. Sulfur trioxide, SO3, combining with water to form the strong acid, H2SO4, sulfuric acid. Most non-metallic oxides are also acids because they act like acids. They react with bases to produce a salt and water in a neutralization reaction. Molecules that have non-bonded pairs of electrons can be bases. Examples being ammonia and water. During an acid-base reaction, the base forms a dative bond with the proton from the acid. Now, when ammonia and hydrogen chloride react to form ammonium chloride, the ammonia NH3 has a lone pair of electrons. The nitrogen, group 15, 5 valence electrons. 3 are used in making covalent bonds with the hydrogen atoms. That's not shown because my emphasis here is the formation of that dative bond with the hydrogen ion. In this reaction, the acid donates a proton to the base, making the base a cation. Yes, it's accepted the hydrogen ion. With ammonia, the cation is NH4+. The acid now becomes an anion, Cl- in this case. Attraction between the two of them results in an ionic bond and the formation of NH4Cl, in this case, a salt. Note, the ammonia, the NH3, accepts a proton and so is a Bronsted-Lowry base. HCl donates a proton and so is a Bronsted-Lowry acid. When a base accepts a proton, it forms a dative bond with it. In order for the base to bond with that proton, which has no electrons, the base must provide both electrons to make a dative bond with the H+. According to the Bronsted-Lowry theory, any reaction which involves the transfer of protons from one species to another is an acid-base reaction. As an aside, because it often causes confusion, the difference between a base and an alkali is that an alkali is a soluble base. It can dissolve in water. All alkalis are bases, but not all bases are alkalis because some bases are insoluble. We could regard our alkalis as a subset of bases. Amphiprotic molecules are both Bronsted-Lowry acids and bases. Some substances can act as both acid and base. What they behave like, either an acid or base, depends on the other substance in the reaction. For instance, if the other species is a stronger acid, then our substance in question acts as a base. If the other species is a stronger base, our substance in question acts as an acid. Amphiprotic and amphoteric have very different meanings. Al2O3, aluminium oxide, is an amphoteric oxide, but it's not amphiprotic. Can't be. It has no proton. Simply put, an amphoteric oxide can react with an acid or a base. An amphiprotic substance can donate or accept a proton. To be amphiprotic, it must have a hydrogen present in one form or another. HSO4- is amphiprotic, as it can donate a proton and become SO4-2. Below, HSO4- is losing a proton, H+, and forming SO4-2. It can accept a proton to become H2SO4. Immediately beneath we see HSO4- accepting that H+ to become H2SO4. There is a trend from basic metal oxides through amphoteric to acidic non-metal oxides, meaning on the left side of the periodic table I have basic metal oxides. On the right side I have acidic non-metal oxides. Between them I have oxides which can behave as acid or base. They're amphoteric. Ionic oxides are found towards the left of a period. These are basic. Covalent oxides are found to the right of the period and are acidic. Amphoteric oxides are found between the true basic and acidic oxides. Again, amphoteric oxides can react with acids or bases. So, in crossing period 3 from sodium Na to chlorine Cl, the oxides formed by sodium and magnesium are basic. They dissolve in water to form solutions which are above pH 7. With MgO, only slightly soluble, and so my pH is 10. Al2O3 is amphoteric but insoluble, so will not change the pH of water. Silicon dioxide, SiO2, is acidic, but it's insoluble in water, so the pH of water would not change. The oxides of phosphorus, sulfur, and chlorine are all not just acidic, but they are all soluble. P4O10, dissolving to give a solution of around pH 1. SO2 dissolves to make a weak acid, pH about 3. SO3 dissolves to make a strong acid, pH as low as 0. Similarly with Cl2O7, the main oxide of chlorine, acidic, pH as low as pH 0. For equations, my two truly ionic oxides, Na2O, MgO, react with water to form a hydroxide. I've shown the reaction with MgO as reversible because it's only slightly acidic. Now, really what's happening here is the oxygen anion, O-2, is reacting with H2O to give 2OH-, characteristic of a strong alkali. It's as if the double negative charge on oxygen and the two hydrogens shared with the second oxygen in water both get shared out. I get 2OH-. My non-metallic oxides, CO2, SO2, SO3, I'm just giving equations for those, combine with water. And you can see in the formula, I'm just combining those oxides with water to make an oxide. They are covalent, their oxides acidic. Last slide. Formation of acid rain. Oxides of nitrogen and sulfur, both covalent, are acidic, and so dissolve in water to form acids. These dissolve in atmospheric water, so the rain that falls is acidic. Nitrogen monoxide is produced from the combustion of nitrogen and oxygen at high temperatures in the internal combustion engine. So as a vehicle moves forward through the air, the nitrogen and oxygen in the air combine to make nitrogen monoxide. This can then oxidize in air to form nitrogen dioxide. Nitrogen dioxide, being acidic, dissolves in water to form a mixture of two acids, nitrous acid and nitric acid. I have the equations there. It can also dissolve in water to form nitric acid only. That's if I've got oxygen present. Sulfur dioxide is produced when traces of sulfur in coal burn. We don't tend to get traces of sulfur in liquid petroleum or in natural gas. The solid sulfur deposits can be removed, but in coal, being solid itself, very hard to remove, The traces of sulfur compounds could be deep within a lump of coal. My SO2 can dissolve in water to form sulfurous acid. Equation given, just adding everything together. Sulfur dioxide is also oxidized by atmospheric oxygen to form sulfur trioxide. This can then dissolve in water to form the much stronger acid, sulfuric acid. Again, just joining the oxide with water. Essentially, oxides of nitrogen and sulfur can both cause acid rain. 2 questions to end with. First one, which species below can act as a Bronsted-Lowry acid in this reversible reaction? I'll pause for a minute. So a Bronsted-Lowry acid is a hydrogen ion or proton donor. On the left, the HCN is losing H plus and becoming Cn minus. On the right, HCN is donating a proton. On the right, in the reverse reaction, H2PO4 minus is donating a hydrogen to go back to being HPO4 2 minus. My 2 acids are HCN and H2PO4 minus. One more. Use the Bronsted-Lowry theory of acids to determine the nature of each species in the equation. I've got HCOOH combining with HNO3, products on the right. I'll pause again. Now, if one substance on the left is behaving as an acid, the other must be behaving as a base. I look at this HCOOH. It's accepting a hydrogen ion from HNO3. My HNO3 is behaving as an acid. Going backwards, the reverse. HCOOH2 plus is losing that proton and going back to HCOOH. In that case, behaving as an acid, giving me the answer C. Hopefully you found that useful. If you did, please hit like, please subscribe for more content.